Hey, it looks like it worked first try. That's always nice. Good way to start off the week. Any questions while we're waiting, folks? Okay. Well, I think we can start. Welcome back, everyone. So today's week is pretty pivotal. We're moving over to working on normal distributions, which seems like a neat trick. It can fit data occasionally to model it well, to finally doing something super important, the sampling distributions using the central limit theorem. We're finally going to bring in the normal distribution to work on distributions that never seemed like they would even qualify. But that's the kind of magic of the central limit theorem. And after chapter 13, we're going to be doing statistical methods finally. Everything is kind of introductory until we get beyond this chapter right here. But any questions at all, folks, about homework problems, the lecture notes, or otherwise? Okay. The other thing to mention is we're also up to week 4, and that's special because that means exams are definitely underway. Our first exam is going to be, looks like, Wednesday of next week. So the exams can get a little bit stressful, I think, in this course. Really, exam 1 is going to be probably your most stressful exam for everyone, since we're getting used to what will the questions even look like. So for our course, I try to put down this document right here to give you an indication of what would a real exam question look like. And here's how I wrote out all these problems. I pretty much just took the same problems that we worked in the lecture notes, wrote them out in an exam format, and this is what they would look like. Some of the things I had to produce graphics for, some of these things I had to produce statistics for. But everything you're doing is really just conceptual type work on these exams. They're the same kind of concepts we worked on the lecture and the same kind of concepts you've seen in your notes as well, or excuse me, your homework as well. So going through this document can be pretty helpful. It's the same problems, but I mean, seeing it again can really hammer the ideas home for the second time. You can go over your old homework problems as well. That'd be a great resource for studying for the exam. We've got a chat. Olivia asked, are we allowed to use a graphing calculator on the test? There won't be a allowed graphing calculator, but the two calculators that are allowed are the TI-30XA. That's a calculator that looks like this one, basically. So your standard, kind of like a lab type calculator. Or if you like a fancier one, I recommend this one. It's got a little bit more comfort features. And for our class, however, either calculator would work just fine. Other questions about calculators or exams at the moment? Oh, that's a great question. I've just written out the exams, so I'm going to be sending the exam information, the roster and such to the testing center to Pocatello. After I send them all that information, they'll reach out to you for times to schedule the exam. So that's going to be underway this week. All the questions about that so far? Okay, thanks for those questions so far, Olivia. Those are the exact pertinent questions you would want to ask for an upcoming exam. One thing I believe we did a little bit earlier in the course was I emailed everyone and decide to ask where you would like to take your exam. Some folks might want to take it here in this classroom. Some people might be taking it in the Pocatello Testing Center. And there's even some folks that are actually closer to an Idaho Falls Testing Center, but they're remote, so they can't make it to class. So if there is a testing center that you would like to be at, just let me know and I'll make sure that that can happen. And if everything just seemed fine with I reached out to you, if you feel like you're in the right place for the exams, then you don't have to do anything further. Well, any questions so far? Okay, so that's kind of how exams will go. And again, after we get through exam 1, it's not going to be as bad. We'll have the right set of expectations. When we come back on this week right here, as was mentioned last class on Thursday, if you have questions about the exam, which would be on Wednesday, don't hesitate to ask. We can always do an impromptu review day on Monday. And those kinds of reviews are mainly student directed. So if you have questions, ask them and we'll get as many questions as answered as possible. Even if we spend the entire class answering questions, that's time well spent. So those are some old problems. I did attach this right here. The exam is closed notes, but there's really not a lot of formulas so far at the moment in this course. But just to give you an idea of a set of expectations, this is something I'll be doing for all of the exams. Even our first exam, again, I didn't have much to put here, but I felt like this could be some good stuff referring to statistics, some information on notation, and definitely the central limit theorem. This would be really our bigger formula, I'd say, right down there. For the upcoming exam 2, exam 3, there'll be more formulas kind of like this, so that it's not, the exam won't be about memorizing tons and tons of technical information. It'll be more about, are you fluent with this information? Do you know how to work with it? Do you know the concepts behind it on an exam setting? So this will be the sheet that's included on exam 1. This is stuff you don't have to memorize verbatim. And other things you could take a look at is, I haven't uploaded it just yet, but I'm going to upload some final exam type problems that's really just review problems for the whole course. And so if you want new problems to take a look at, they'll be posted down here shortly before we come back from our weekend of this week. So that's pretty much where we're at. That's where our plan is so far. Any questions, comments, or concerns at the moment? Okay, well, I think we're ready to get going. We mentioned that chapter 13 is kind of abstract, so we looked at a simulation of what it's all about, but now we're going to start it in earnest. On these notes, first page is kind of informational. We'll get through it slowly, but the theme that we looked at is essentially this picture right here. So understanding this chart is one of the big takeaways of this whole note, all the notes here. Before we delve into this too much, there's a couple questions. Oh, that's a great question, Cindy. Yes, chapter 13 will be on our first exam. Let me go back to the exam information. It's going to cover chapters, oh, sorry, my window's kind of lagging. It's going to cover chapters 1, 2, 11, and 13. And Zach asked, we won't need to memorize any formulas. There'll be certain formulas that you do have to memorize, but anything that's on here is the list of things that you'll have included for the exam. So I don't think there's any major formulas aside from what's inside here on exam 1. But for upcoming exams, there might be a couple things here and there that you do have to memorize. Does that answer your question there, Zach and Sydney? Okay. Oh, for that question there, calculating the interquartile range, that was a question that I never made you specifically calculate. Or hang on, let me think about that. I think that was something that we did calculate. Yeah, that was one we would have to memorize. So that'd be a formula like this right here. IQR being quartile 3 minus quartile 1 could be potentially an exam 1 question since it's not on the list right here for the formula sheet. But a better exam 1 question would be more along the lines of knowing what this actually represents, knowing that this is the distance for the central 50% of the data set is almost more important than the computation right here. There's a good chance that if I did include that on exam 1, I would probably just give you the actual value and you'd have to interpret it. Other questions about that so far? Okay. Well, there's lots of great questions about the exams. Thanks for asking all those folks. And if another question comes up, whether or not it's a chapter 11 or maybe a homework problem or exam question, don't hesitate to interject. Sometimes that's just what happens. We'll try to get those questions answered as well. So for the moment, we're right here. This is a pretty big wall of text, but this is meant to be just an illustrative example right here. So it's not as bunch of stuff as it seems like. We're starting off chapter 13 with a reminder of 2 massively important definitions in statistics. The definition of the population and sample, as well as their corresponding parameter. The parameter is always something that describes a population, and the statistic is something that describes the sample. So you'll know you're dealing with a statistic if it's a number that's describing, say, the number of individuals that were collected or surveyed or anything along those lines. You'll know you're dealing with a parameter if it's introduced in a way that's talking about everybody, a national value, or everybody at a college, anything along those lines. Now we're dealing with parameters. In statistics, these are typically unknown. For inferential statistics, the whole goal is to estimate them. And here's how we can make it happen. So here's our example. Suppose a population is all ISU students. So that's a familiar population that we care about. And notice how undefined that truly is. Does that mean students currently registered, undergraduate students, graduate students, both? All sorts of things can get conflated in that. So when you define a population, sometimes you have to be extremely specific. But for the sake of an example, let's just leave it like that, all ISU students. So we're interested in this parameter, the average GPA of all ISU students. Now, if you work for the university, you probably have means to access that if you need that information. But if you're a competing university, that might be good information for you. You might decide, here's how we're going to draw away ISU students. Let's get some basic information about, say, the GPA of all ISU students. The researcher is going to have to select a random sample because there's no way they can contact everybody. That study would be so costly that there'd be little value there. So they might settle for, say, 100 students. Once they have those 100 students, X bar is going to be the GPA on the average GPA, that should be said first, mean GPA of all ISU students in the sample. So that's what makes this one a statistic. It's describing the sample. This is the unknown describing the parameter, but after completing the study, we get this estimate right here. Now we know there's a couple problems with this estimate. We hinted at it in chapter 1 that there is no information right here about how certain that approximation is. Another problem is the actual sample that we pulled, the 100 students, could be fundamentally flawed. That sample has to be representative of the target population, all ISU students. So if they got, say, 100 students from the Idaho Falls campus, folks in Zoom would probably agree that there's no way that they're going to be fully representative of people who live in the Pocatello campus and go to school there. Your experiences really are different, and that's going to shape your personalities and all sorts of other stuff. So if we need a representative sample, that's where we start to talk about randomization. But first, a sample is representative as long as the statistics that you calculate from it accurately represent the corresponding population. So that statistic here may or may not accurately represent the entire population, or in other words, be a good estimate of the unknown parameter. If we have a representative sample, then we have more confidence. And this is the gold standard. Unfortunately, it's not always met. Sometimes it's actually quite hard to get a simple random sample, but when it can be done, our procedures are the most powerful, and those are going to be the major procedures we're describing here in our statistics course, procedures where the data came from a simple random sample. Here's how the definition goes. A simple random sample of size n is a sample in which each set of n individuals in the population has an equal chance of selection. Now, that's a heck of a statement right there. I think it takes some unpacking when you read it the first time. But this is what makes a simple random sample. Here's an example to kind of give us a feel for that definition while we're considering it. It says here, imagine we're trying to get a simple random sample in this situation. There's a lecturer teaching a large class of 350 students, and the teacher says they're going to sample the class by rolling a die. Now, this could potentially work as a simple random sample. However, here's how we're going to start off. Starting with a row number on the die, so you'll roll a die, maybe it lands 5. We're going to pass out a survey to every 4th row of the lecture hall. So if I roll a 5 on the die, 5th row gets an entire survey, then the 9th row gets a survey, the 13th row gets a survey, and so on. The lecturer says, this is a simple random sample because everyone had an equal opportunity to sit in any seat, which is true, right? You would have had that opportunity, although people fall into a pattern after a while. Let's imagine people are sitting completely randomly in this large lecture hall, and because the choice of rows was randomized. That's true as well. The die is randomizing the choice of which is the first row and then the 4th row thereafter. It turns out for that question, this is not a simple random sample. So let's start by just spilling the beans on this one. No, this is not a simple random sample. Now, there is randomization in this sample, so it could very well be representative. The statistics working with this might be harder. However, let's also focus. Anyone see what wrong here? Why is this definitely not a simple random sample? Anyone see what the conundrum would be? Really kind of subtle. So if you're not sure, no worries. If you think you've got it, but you're not too sure if it's right or not, no worries. You can throw it out there, no judgment whatsoever. In the chat, someone says, is it because they could teach several classes? It's not so much the different classes on this one, but it's something a little bit different along those lines. Thanks for contributing that. Other questions in class? Look like you have something on the tip of your tongue. Each individual? Well, you would have a chance of being selected. You just have to sit on the right row that was selected, for example. So, for example, if they, on this one, on their first roll of the die, let's suppose row maybe 1 was selected, then if this was the class where that's happening, you would have been skipped in that case. If row 3 was selected, then you would have been included, but the person directly, well, the people directly behind you cannot be included any longer, right? Because we'd be selecting row 3, then we'd be selecting row 7, and so on down the line. That's where this comes into play. If we select row 3, then you are included in the sample, but the gentleman behind you would not be. And so there is samples, including, say, the people behind you, you yourself, that would never be part of this random sample, since we have, by design, a requirement of skipping rows. So if a sample of certain people is impossible, that's what excludes this from being a simple random sample. In other words, we could say this is not a simple random sample, since no sample includes students from consecutive rows. So that's the whole problem on this one. If you can't have people included from, say, row 3, row 4, and so on, well, it could still be a random sample. It's still useful, but it's not this, the simple random sample. Felt like it's a good one to spend some time on, since that is definitely kind of a weird type of mathematical thing going on here. Does it make sense to focus on that feature right here for random sample? Okay, so a random sample means you have to think about what are all of the possible samples. Now, this is a very large number, even for a class of, say, 350 students. There are lots of specific samples of, say, size 50 or something along those lines. So we have to imagine what are all the possible samples, and every one of them has to have the same chance of being selected. If you can make all that happen, you've got a simple random sample. It so happens that technology is really great at simulating this with pseudo-random numbers. And it asks, so would it count as a simple random sample if they accounted for all rows and gave every student survey, but only use the data from every 4 surveys? I think, let me think of that one. That one might have the same kind of struggle where you couldn't have data from consecutive surveys. So that would be a sample that would be excluded in that case. Does that make sense with that question there? Yep, gotcha. Absolutely. And let me ask a question for the class. Now that we're talking about this and the weird things that can go wrong with what looks like a good sampling design, should we simulate our own simple random sample? Does that sound like something that'd be kind of fun? How about we do this ourselves? Let's show how to do a simple random sample of 350 students. Now, there's potentially some philosophical positions you might take on how true of a simple random sample this really is, because I don't have true random numbers. I'm going to be using software, so we're using pseudo-random numbers to simulate a simple random sample. Think of it along those lines. You can make RStudio do the work for you, but For this, let's actually use Excel. It's a little bit more visual to see what's really going on. This is more of a demonstration, not something that you would be expected to do in class, but think of this as something to just get a feel for what's a simple random sample, what would it look like, or if you had to implement this in a different class, this might be what you actually do in fact. You might use different technology, but our Excel, again, is just a little bit easier to visualize for us. So here's our Excel to start. Maybe we'll zoom in on this a bit. First thing we need is a sampling frame. We want a simple random sample, but all that's referring to is a list of everyone we care about. So let's start by going 1. That's just going to refer to student 1 at this point. Let's go to the prior cell, add 1. So here's student 2. And we go all the way down to, say, it said 350. So there's 350 students. These are the identifiers. Think of them as student numbers or something along those lines. We want a simple random sample. Next thing I need is, well, definitely some random numbers. If you go equals rand and just a parenthesis, we're using technology to get a pseudo-random number between 0 and 1. So that's the first number. Let's take this. Here's a weird trick someone taught me in class. If you double click right here, it propagates that all the way down to the very bottom. So everyone has a unique random number. Those numbers change all the time, anything you do here. So type in a letter, delete the letter, and it changes, but that's actually okay. So now let's say we need a sample size. We haven't thought about that. How about sample size 10? Just something easy to visualize. Gather a simple random sample of size n equals 10. So that's going to be our job. Easiest way to do that is just highlight these 2 columns that already has the random numbers. And we can sort column B and column A together based upon column B. Let's go to data, sort. Let's go sort by column B. Smallest to largest or largest to smallest is irrelevant. These are truly random numbers. Hit OK on this. And oh, I broke that. Hang on, it's Control Z. I forget that there's a formula inside there, isn't there? There's a trick to this. Copy it. Oh no, don't do that. Copy and then paste it as just digits. That way we wipe out the formula. It's turning into a longer demonstration that I thought I would turn into, but here we are, we're almost there, folks. Okay, so we have students, we have random numbers. Next thing we're going to do is sort the random numbers here. We're going from column B, smallest to largest, and there it is. So these first 10 students are going to be part of the sample. We did it, folks. That's our simple random sample. And to just tie up the statement, students 226, 146, 207, 30, 300, 242, oh, that's not quite right, 242, 14, 343, 116, 138 are part of the sample. So we did it, folks. That's the simple random sample. And this would do a great job. Looking at the numbers, there is nothing preventing from consecutive students, every 5th student, or whoever to be in the sample. And this really looks like they were truly randomly selected. There's no structure that's prohibiting any one sample. Probably all samples really would be equally likely in this process. Any questions at all, folks, with the simple random sample ideas? Okay. Again, only reason we bring all that up is making that estimate right there by the red dot is finicky. We have to describe the error in making that estimate, doing that later on when we're dealing with confidence intervals. But that equality there could be fundamentally untrue in the first place if the sample was never representative. So simple random sample is, again, our gold standard for getting quality data where we can be more sure that the equality is accurate and makes sense. Well, we did it. That's our random sample. Once we go beyond there, this page is more kind of just informational. There's a lot of things that we're going to be delving into in this class. Let's blow this up. We've already talked about the statistic X bar, its associated parameter mu. We've also talked about the standard deviation S, its associated parameter sigma. And if you want to calculate some of these, that means you're not doing inferential statistics, you have accessed the entire population, and you would be using this new variable, which will be very rare in this class since we're often not having access to a whole population. But if you did have a population to work with and you wanted the mean, you would use uppercase N there. For the new statistics and parameters, if we're dealing with categorical data, specifically with two outcomes, we'll be using this as a statistic, p hat. And this would be the parameter just p. So that's something that's coming up pretty soon. So let's actually make a note of this. This is for categorical with exactly two outcomes. The outcomes generically are called either a success or a failure. And so we're interested in the successes in the sample. So when we get to those kinds of parameters, that's what we'll be looking at. And another reason of bringing this in is we're only doing a part of chapter 13 that's most relevant right away. We're not going to do the part of chapter 13 that goes to sampling distributions of p hat. But just to talk about it, here's what they would look like as a statistic. Any questions, folks, with the notations down here? Okay, this is a lot of stuff, but I wrote this all out here just to be kind of a one-stop shop for where to go and get statistics and parameters if you need to look those up. And here's our example one right away to practice with this. This one is actually similar to example one at the very, very start of the course. What we're trying to identify here is what is the parameter and what is the statistic? And that's going to be an exam problem as well. So I felt like we might as well practice it here and now. So here's how it goes. It says, after hearing of the national result that 44% of students engage in binge drinking, defined in this way here in parentheses, a university administrator surveyed a random sample of 244 students at his college, found 96 of them admitted to binge drinking in the past week. So that's the context so far. And we've already have a lot of numbers going on here. But it goes on to say, in this description of data, indicate what is considered a statistic and what is considered a parameter. We'll use the correct symbols and explain our choices. But before we do any of that, reading through this problem, we should also decide what kind of data is this even in the first place? Would you consider this description of data to be categorical data or numerical data? Olivia says categorical. Yes, absolutely. Good call on that one. There's actually a pretty good giveaway for this. Notice as you read through here, there's really no units. They're not measuring time, distance, any kind of things like that. But what you did get is percentages or potentially proportions if they're change the unit on us. That right there is enough of a giveaway to say we're probably dealing with categorical data, much like what's indicated here. That means these would be the symbols we would be using for the statistic and the proportion. But for the upcoming exam one, I'm going to ask a question like this that's more similar to chapter one, since we haven't done as much work with p hat and p as we have with x bar and mu. So your question will be more similar to that one at the start of the course. So this is already telling us we're dealing with categorical. And if it's categorical data, that means you're just taking all your students and classify them into two categories. A success here would mean the student did engage in binge drinking. That sounds morbid, I know. And a failure would mean the student did not engage in binge drinking. This is something that's going to be common in statistics. Something to refer to as a success is just the thing you're looking to study, which is not a good actual outcome for the individual all the time, like engaging in binge drinking. That's a success because that's what the study was interested in, not because it was a healthy lifestyle. So that 44% says we have categorical data. That definitely gets us started. We can write down a p hat for the statistic and a p for the parameter. Now, here's what's really weird about statistics at the moment. P the same one that we wrote over here, is not 0.44 or 44% if we change the unit. That's a whole different parameter. This gets kind of weird in a certain sense, but it's something we have to get used to. So this is one of the additional reasons we're studying this problem. Sometimes when we do inferential statistics, there are multiple populations we're trying to consider all at the same time. So that 44% right here, that's the national result for students engaging in binge drinking. So we're looking at a overall larger population of everybody in the nation. We're assuming possibly USA when we say that. But then once we go from that 44% to this information, we are looking at a random sample of 244 students at his college. Now that's a second population, the population of all students that belong to one specific population, not the nation any longer. Probably the administrator is wondering, is his college similar or dissimilar to the entire nation? So now we're comparing populations in that certain sense. So when we go to write out this P, it's definitely not 0.44, but maybe it is, maybe it's close. I would say the college is similar to the nation, or maybe it's way low, or maybe it's way, way higher. And that would say the college is very different from the nation. There's something special about that one college. But in either case, this is the hard one, writing out P. So let's do this and say P equals the population proportion, or you could say the percentage of the population rather than population proportion. It'll be the population proportion of students that binge drink at this university, or college is what they said. This college is say, we're not talking about the nation, but that one specific college. This one is very tricky in my opinion. We'll get a lot better at it as we practice statistics, but it always takes a little bit of extra practice at the start. Does that make sense to folks on what we wrote down there for P? Okay, we're happy with that. The statistic is not so bad. It says indicate which is considered the statistic, what's considered a parameter. We use the correct symbols and explain our choices. Here we could say that that's our P, since this describes the population and so it's a parameter. So that's our explain your choices there. I forgot to read the whole explain, so let's pen that in just to fix it. Now for this one, P hat, it's not so bad. For P hat, we take the number of successes in the sample, divide by the sample size. Has anyone spotted what the denominator should be for the sample size n? Absolutely. So from right here, that's our sample size. Only write these out. Not a bad idea to just pen that into the margin. N equals 244, gets it into your head so that when you go to write out your statistic, your brain probably already just wanting to fill that in right here. So 244 goes in below. Once I get my penmanship sorted out. So we had 244 students that were selected, and here are the successes. 96 of them admitted to binge drinking, so 96 goes here. And that's our statistic. We want to explain our choices. Let's say here, this is the statistic. Since it describes the sample of n equals 244 students. What we did, folks, that's our breaking down this problem, finding the statistic, finding the parameter, which is a little bit harder. Now that we're looking at, let's take a peek at what this statistic evaluates at. It was 96 divided by 244. So it's at about 39%. Now, a university administrator might see that and say, huzzah, we're doing really good. Our students are very, very responsible. Look at that. They're below the national value average of 44%, or the not average, the national percentage of 44%. But as a student of statistics, you have to be the one to tell the university president, hang on, that's not quite right, because when we go to estimate, this p being approximately equal to p hat, we're right back into this situation. We're just putting p here and p hat. There are a lot of problems. We have to ensure we had a representative sample. We can trust them on that, but there is also an error in that estimate. That error could be so wide as to actually encompass 44%. Then your university is no different than the nation if the interval that contains our estimation contains the 44%. That's something that we'll detect here and there. So you can never get excited about the data until you actually do the statistics. And Olivia says, so this is not a representative sample. I'm not too sure on this one, whether it was representative or not. Let's see what they said. They told us it was a random sample. So that gives us some good hope that it really was representative. They didn't specify the randomization. And if we really looked at the study, we would probably have to see exactly how they carried it out. As a student of statistics, all of our problems are going to be really, really short like this. So if they tell us it was random, we'll just trust them. We won't try to necessarily find the study and ensure it was. But other questions about that so far? Okay, so far chapter 13 is kind of like chapter 1. We're thinking about statistics and what we're trying to achieve. And this is looking at the first example of the course from a different point of view with categorical data. So we'll try to do inferential statistics for both types of data. And it turns out whether or not you have quantitative data or that scenario with categorical data, two outcomes, the central limit theorem and so thereby the normal distribution, they're still in effect for us. We can use normal distributions in certain settings for categorical data even, which is surprising. But here's our big picture that tries to get us closer to what we mean by sampling distributions. First remark I want to make is this came from this textbook right here. It's a great textbook, but I think it's more advanced for a course like this one, which is usually a first course instituted in statistics for most of us. If you like statistics and know you're taking more, this could be a decent one to look into. And it contains really nice graphics like this, main reason to use it. They do use a Y bar. So think of X bar is Y bar on these notes, and you're not doing anything different. So here's the idea. When we say sampling distribution of a statistic, whether it's X bar or P hat or any statistics whatsoever, we're talking about a brand new probability distribution, much like a normal distribution. And what that will contain is all of the possible values your statistics could ever take. So if we are back here in the land of, say, quantitative data, this could be your population. There's a true average mu there, a true standard deviation sigma, and this is what one study is going to achieve. It's going to be selected with a sample size of n, and it calculates the statistics, y bar or x bar and s. We're focusing on the statistic y bar and its sampling distribution. Once you calculate that one statistic, you just take that value, and there it is. That might be what you reported in the study. But when we were considering sampling distributions, we are asking the question, what would happen if we took a simple random sample of size n infinitely many different times, never ever stopping, until we have every possible sample that could occur, and now we're dealing with every potential sample mean that would ever result from sampling in this population. That's the sampling distribution, and visually, here's what it looks like. Imagine you sampled again. You calculate a separate y bar. There is no reason it's going to be the same. You have a different set of individuals, almost guaranteed. And so your sample mean is going to be different. Plot down there, keep repeating over and over again, and you're going to aggregate your sample means into a display like this. It's quantitative data, so we'll throw it into a histogram. And the dots down here are saying, oh, that was a weird button I pressed. These here are saying, don't stop this process, keep repeatedly sample at sample size n. This is not something you could really do, but it's something that you could consider. You could write a theorem about what would happen if you did this. And this is what would happen. Your sample means are going to start to look like this if your sample size is large enough. And it doesn't even matter if the population is distributed normally. In fact, it could be distributed tremendously skewed. For a large enough sample size, all of your sample means are going to start to look like this, end up in that kind of situation, which means they could be suddenly well modeled by a normal distribution. All we need to know is, where is the center? The center ought to be the exact same center as the mean of the population. And it turns out that is true. When you go to sample and get just one mean, you're taking a separate sample from here and pulling out any kind of mean that's close to that central value, the true mean itself. The one thing that we don't have is what is sigma actually equal to? The central limit theorem will tell us it's equal to this thing, the standard deviation of the population, divided by the sample size n. This is kind of clunky to look at, right? We're trying to describe a sigma for this population. It refers to a sigma from the underlying population. How do we get around that? Subscripts. They're ugly, but they work. So sometimes we might say sigma of x bar if we need to avoid a conflict notation. That means we're talking about the mean of this right here, the sampling distribution of x bar itself. Well, that's the picture of what's going on when we're dealing with the central limit theorem. Any questions at all, folks, with that picture there? Okay, let's start practicing actually working with it and see where we're going to end up on. First, this theorem right here. Oh, I shouldn't skip too far. Oh, that's about right. First, this theorem right here is not the central limit theorem, but it's still a pretty nice theorem. It gets us close to what we need in the central limit theorem. In fact, if you read this carefully, there's really only one problem here. It says, gather a simple random sample. That's good. We want simple random samples or randomization of any form that's distributed this way. So the only way to use this theorem and get a concrete answer is you had to know your underlying population really is exactly normally distributed. Otherwise, this theorem just doesn't work. But if your population is normally distributed, then the sampling distribution of the sample mean x bar would also be exactly normally distributed. That part of the statement's nice, but it means this is really more of a math problem unless someone says, just trust us, the population should be distributed normally. That's a suspicious claim, and so that's why this theorem is really not the final form of what we want. But still, we should practice with it. Think of this theorem as bridging the gap between chapter 11 and where we're at right now. It starts off by saying, let me know if I pronounce any of the stuff wrong, incorrectly. Serum alanine aminotransferase, I'll just call this ALT from now on, is a liver enzyme. And this is why we should care. Elevated ALT can suggest a patient is suffering from viral hepatitis, diabetes, congestive heart failure, and much more. So if you're struggling in some way, that liver enzyme could be elevated potentially. Now it goes on to say, a certain test for the presence of ALT is rather imprecise. The results of repeated tests of a single specimen follow a normal distribution. Let's just trust them on that, but that's what they're saying here. There is an exact normal distribution somewhere in this process. The mean is going to be equal to the true ALT concentration for that specimen. Let's just put a pin in this thought. The mean is the true ALT concentration for that specimen, and it would go right there as soon as it's stated. The standard deviation is 4 units per liter. So this will be the value sigma. It goes right up here, and then you divide by the sample size square rooted. So that's where sigma is going to end up. Next statement it says is, suppose that a hospital lab measures many specimens every day, and specimens with reported ALT values 40 or more are flagged as unusually high. Okay, I really don't know what to do with that yet, but let's just highlight that and keep on going. Next it says, suppose that a patient's true ALT concentration is 35 units per liter. That ties together with the statement above. So we're talking about the true ALT concentration. So now at this point, we've discovered the value of mu. We can say mu equals 35 units per liter. Finally, it says, let X be the test result for the presence of ALT. So X is not going to be the true ALT of the patient. It's just going to be the measurement after running it through the test, all the diagnostic equipment. Well, we got through it, folks. This is kind of a nastier statistics problem, in my opinion, because the context is pretty technical. It's talking about some severe things that could happen and such. But also the way the information is presented is kind of nasty as well. This happens in statistics when sometimes if you're interfacing with someone that doesn't speak statistical language very well, they're going to give you information that's all over the place. And this is a skill for you. Stitch it all back together, discover what they're really talking about. We wanted the parameters mu, this one, and sigma, this one. Sometimes we have to take work to get those out. But one promise is I'll never do that on a real exam. I'm trying to make the actual real exams a little bit more straightforward, where we're not trying to unwind things. This is pretty decent for a homework question, though, unfortunately. Well, first question they ask right out of the gate, what is the probability distribution of X? This is going to be a question that you'll see in the notes. It comes up in the homework, and it's going to come up in exams as well. This is always a tricky question. But really, you can answer it by starting with X. Tilde is going to be saying is distributed as, and they tell us, well, X is a test result, and they follow a normal distribution. So we can put that in. X is normally distributed from that information. Once we state that, now we're going to pull in what we found in the problem by going through the reading of it. The mean is going to be the true mean of 35 units per liter. Now, we don't actually know that, but this is more maybe the medical professionals thinking about their test, and they're saying, well, suppose we did have this kind of patient. It's more of a theoretical question at this stage. What would happen to this patient whose true ALT is 35? Next, we have to give it the value of sigma divided by the square root of n. Sigma is 4 units per liter, but we're taking a sample of size 1. So really, this is kind of irrelevant in a certain sense. If 1 goes there, there's nothing to use. We're not really using that theorem because we're dealing with just X. So 4 would go right exactly there. Finally, that's its probability distribution. And now in part B, we're going to work with that probability and so on. But any questions, folks, on getting that statement down? Okay, now that we have that, it says, find the probability that this specimen will be flagged as unusually high. And I think we have something there. It says 40 or more flagged as unusually high if the reported value is a result of a single specimen or single test result. So if they're talking about one single test result, we're talking about X here, and we're not using anything fancy, just this distribution. So the whole question can now be rephrased as, what is the probability that X being flagged as unusually high is 40 or more, so X larger than 40? From our practice in chapter 11, this is going to turn into a p-norm function, but here's a really quick graph. I'll put here the center of 35. Then if we could move over by about 4, we're at 39. So 40 should be right around here. So our answer to the question is going to be that area. And because we're still just practicing the normal distribution, let's write this out carefully for the notes. That area, which is also the answer to our question, is p-norm, throw in 40, 35, and 4. Then one more input. We're accumulating area to the right, so we also need to set lower. dot tail is false. So that syntax is going to get us that area. So let's convert over to RStudio and do our first computation of the day. Okay, just got to figure out a place to put this stuff. That ought to work. As before, it's a good idea to just start by indicating your parameters. Mu gets 35. Sigma gets 4. Then for this portion, I'll put just a quick statement. If you hit Shift 3, this is something that won't evaluate. Let's call this part A. And it's going to be P norm 40 mu sigma lore.tail set false. So that syntax should do it for us. Let me know if you're getting any kind of issue or different numbers. When I run this, I'm getting a probability of, let me move that over a bit, 0.1056. That look right to folks so far? Okay, it looks like we're happy with this one. So 0.1056 goes in. And we did it, folks. That's our computation right here. Well, we didn't actually use our theorem. The point of this question is really for us to tell when we're using something new or when we're doing something exactly as in chapter 11, for example. This is strictly a chapter 11 problem. And then once we go to part C, we're going to change it into a chapter 13 problem. And it'll be very important for us to spot what made it a chapter 13 problem. So think of this as a kind of compare contrast type of a question. But also looking at this, a practical interpretation wasn't asked for it, but if you read it out, you would say there is a 10.56% chance that the test result will be flagged as unusually high, bigger than 40, when in fact the true patient's ALT was 35. So for these patients, we have a 10% chance of calling them back into the office with some potential medical problem, and that person is totally fine. They really don't have an elevated liver enzyme, not the ALT at least. So that's kind of rough in a certain sense. Now we're wondering what would have happened if, instead of a single sample, assume we have a random sample of 3 tests from a single specimen. Getting that kind of random sample might be a bit of a thought process, but assuming we really have it, we're wondering what should happen to that probability. Should it go down by a little, a lot, be about the same? It says we're going from one observation here, just X, to a sample of 3. So we might decide maybe it gets reduced by a third or something. But the real answer to that question comes from here. We're now implying the sample size is 3, which is going to change this right here. The entire standard deviation of this model is going to cause that curve to come in closer, and it influences the probability by sometimes a remarkable amount. So let's try it out next from this point of view, where let's take a screenshot because we will be using this theorem now, this almost central limit theorem. Okay, so same kind of question. Assume we have a simple random sample of 3 test results from this single specimen. What is the sampling distribution for the mean of this sample? Well, this question is kind of like we asked here in part A. Turns out probably the most important thing to pay attention to is that word right there. We're not talking about single observation. We're talking about the average of multiple observations. So we write out this. X bar is distributed. It'll still be distributed normally, like when we're talking about the single specimen up here in part A. It still has the same mean. And our statistic is fundamentally flawed, right? If the center was anywhere but 35, which is the center from the underlying population. So 35 has to go here. And it turns out it's also correct by the theorem. Next, we take sigma, which is 4. Let's throw it in about right here. And this is the new step. Because we're talking about X bar, because we have multiple observations we're working with, 3, we use this part of the theorem and divide by the square root a 3 right there. So this is now our new model, and we have to be really careful now when we go to calculate probabilities to include the root of 3 right here. That's probably going to be an easy thing to miss, even if we knew it was coming. That's easy to miss sometimes. But if you put this down here, then there's definitely going to be partial credit. I know that you would have just simply forgot that right there. We did it, folks. That's the complete use of that theorem. And now part D says, find the probability that this specimen will be flagged as unusually high if the reported value is the mean of 3 independent assays or tests from the same specimen. Same specimen means 35 here is still valid. We'll include the probability statement in this answer, like we did on the prior one. And this time it would go like this. Almost exactly like what you did in part B, but it would go probability that the sample mean, or X bar, is greater than 40. It's pretty much the same exact picture right here. We're just making a change in that location. Let's write that out just so it's apparent in the notes. Here's my very flat normal distribution. It's still centered at 35, but the shape of this curve is different than this one because of this right here. The spread has gone down by a substantial amount. We're still putting 40 somewhere, but you know what? 40 is probably going to be further to the right because it became less spread out. We just don't know by how much, but whatever our answer is, it's still going to be calculated this way. P norm, we'll give it the value of 40 from right here. 35. We make one adjustment here. It's 4 over the square root of 3, coming from this part of the model. Then lower dot tail is false. Lower dot tail equals false. So the moment we get that area, we're ready to go. And if you have a number in mind, then that's going to be awesome. We're going to see how much this dropped by just pulling in 2 additional pieces of information. If you haven't guessed yet, then give it a try. Let's see what we're going to get. So everything here, I probably wouldn't make too much adjustments, but might not be a bad idea depending on how you write this out. I usually put in the sample size if I know I'm using this kind of theorem. We have n equals 3 or n gets 3. Now this one is for part D. And I guess that is technically part B, isn't it, on that one? So almost the same thing, go P norm, 40, mu, and sigma. This is where a really simple mistake can sometimes occur. Be sure to divide by square root n right here. You could modify this one and make it work out, but if you separate it all out, you probably are thinking of writing out the work this way with your syntax. Last, lower dot tail is false. And this should do it for us, folks. Oh, let me control Z that. There we go. It came down to this value. We went from over 10% of being flagged as having an elevated liver enzyme, a serious one, and that's on one piece of data. Add 2 more pieces of data, so we're at a total of 3, and it's dropped down to between 1 and 2%. It's a huge drop, pulling in that extra information. So it's a 0.0152. Let's use a more official pen for that. 0.0152. Let me double check my numbers here. Okay. Well, we did, folks. That's using this theorem up above. It's practically the central limit theorem. So this gives you a good feel for what does central limit theorem computation really look like if you're in a homework setting. Any questions at all, folks, on getting through this one? Okay. Again, it should feel kind of like a chapter 11 problem, but watch out for any question that could potentially be talking about the average of multiple observations. It might say average or mean. This right here is also a giveaway. If you're not talking about a single observation, multiple observations, then you're modeling this way, and your probabilities will come out very different with that change. Well, that's the central limit theorem almost. Like we mentioned, The worst part of this theorem, the reason we're not calling it the central limit theorem we want to use, is right here. The moment we require the population to be distributed exactly normal, we've almost eliminated just about everything worthwhile from actual physical practice until we get rid of that statement there. And here's what it looks like. This is pretty much re-saying what we were saying before. The previous theorem is of very limited value, but this theorem is extremely important. I wrote here just as a quick blurb. This is a deep result of probability theory. It's such a deep result that if you go to graduate school in statistics, you probably are also going to require some masters in mathematics. This is some of the most hardcore real analysis ever, and probability theory rolled into one. A book about this size could be dedicated to this one fact. The content and behind the proof of that theorem could be a lot of reading. But people delved into this. This was discovered hundreds of years ago. And here's the theorem. This one is extremely applicable to the sciences, real world data. And it's because of this statement right here. This works for any population. Your underlying population could be absolutely terrible, and we'll look at one, but the central limit theorem still works. It's a pretty freakish fact about our reality. It says this: we still want a simple random sample. If we mess that up, we are messing up this theorem. But after you have a simple random sample of size n, doesn't matter what the population is, it's just required to have a mean. Some populations may not have a mean or a standard deviation. There's some weird populations out there. We're not doing those pathological ones. But if you have an actual normal population with a true mean and a true standard deviation, then if your sample size is large enough, in other words, for large enough n, the sampling distribution of x bar is approximately that. The true but unknown mean will go right here. Standard deviation will go here. We'll divide by the sample size in that location. Well, any questions, folks, about that statement of the theorem so far? Okay, so this theorem tells us we should expect a lot of normal distributions, even from populations that we would never saw them coming. I do have some rules of thumb because this is the hard part of the central limit theorem. What is a large enough sample size to get decent accuracy? First, here's a super blunt rule of thumb. This is not bad for textbook work, but it starts to not become great once you're doing a lot of stuff beyond the class. But here it says, the more skewed your original population is, the larger your n must be for the original approximation to be accurate. And if your sample size is greater than 30, the central limit theorem can be used. Again, that's a very, very blunt rule of thumb. The author who wrote this says and admits there are populations for a sample size of 40 and 50 is not going to work, but those are rarely encountered in practice. That is his opinion, so you should always take that with a grain of salt. This is a probability textbook as well, but this is a pretty decent one as well. So usually a sample size of greater than 30 is going to be pretty okay. But I want to show you a population where it's not okay, where things can go really, really astray for us. Any questions or comments at the moment? Okay, so far, this is practically the theorem we just used. The only thing we took away is a stringent requirement that the population is normally distributed. So now let's practice this again. This is the only theorem I'll ever put in a box just to signify its importance. And this example 3 came from this textbook once again. Felt like that textbook really talked about this central limit theorem well, as opposed to ours. It says here, a psychologist measured the time required for a person to reach up from a fixed position, operate a push button with his or her forefinger. So this is a psychology experiment, and those are always weird. You will go into a psychology experiment, if you haven't done one before, they'll tell you what you're doing, and then after you've done everything, they'll tell you what it was really all about, and you'll find that what you thought you were being tested was not at all what the test was about. Probably that's what's going on here. People probably were thinking, oh, the researcher is measuring just how fast I can hit the button. And so lots of weird things can happen. A lot of people hit the button right around here in milliseconds. And those were probably the people who were pretty calm and they were not too flustered. But some people maybe on their first push of the button, they got a little excited, they missed something like that. They push around between 400 and 600 milliseconds. That's a substantial amount of lag at that point. So we have a distribution which is what the author said is violently skewed now. This was really a histogram where a smooth curve was just put over the data so that we're looking more at the curves, less at the teeth on the histogram, for an example. So think of this right here as the underlying population. The population's mean came out at 148 milliseconds. Standard deviation was the 105 milliseconds. And now, let's imagine that we took this population right here and started sampling directly from it. So take a random sample of size 4 from the underlying population above, calculate the average, and this is what the sampling distribution of the statistic y bar or x bar, let's write that in again. Y bar is referring to x bar in these notes. Here's what our sampling distribution would look like in this case. Let's zoom in on that a bit more. It seems about right. The larger your sample size, the more your underlying population, no matter how skewed, is going to start pulling in. That's what the central limit theorem is doing for us. But a sample size of 4 is really not great for us, and neither is 8. These are still right skewed distributions. These still have multiple peaks. They're multimodal distributions. And so this statement, for large enough n, the sampling distribution is approximately normal. Not quite right. That's pretty off. The sample sizes were just too low. It was less about the underlying population. The central limit theorem will still work, even for this. Again, it's violently skewed, something that we wouldn't want to see necessarily in our data, if we can help it. So at sample size 4, sample size 8, central limit theorem is not going to work for us. But the larger and larger your sample sizes get, here's what starts to happen. Symmetry begins to appear. The multiple modes that you see here, the multiple main peaks, start to wash away. But one thing never changes. Mu is always going to be in the same spot right here. The peak, notice, is starting to center around it. Here, the main peak is a little bit to the left, starting to aggregate around here. And now at this stage, we're getting pretty close. That actual curve is peaking right where it should be in this for the normal distribution. This is at sample size 32, and here you'd have to make a judgment call. There is still some skew here. Some folks would say, if we're using that rough rule of thumb, that this is okay, that there's not enough asymmetry to cause a problem. But I would say, if you really wanted accurate data, you probably should be right around here. Sample size 64, we have much more symmetry. You might say, why not just go for a sample size of 128? Well, they should go for a sample size of 1,000 if they can, but one thing that's kind of sad about studies is usually we are constrained between accuracy. We don't want those, but also cost. We don't want to pay for a sample size of 128. Sometimes we settle for good enough. We have accuracy and it's affordable. So this would be a great stopping point here. At size 64, the central limit theorem looks like it's effective, and we're not going to deal with a super costly study. But that's what the central limit theorem looks like. And again, big takeaway from this problem right here is really just about that rule of thumb. Our author admits that at sample sizes 30, central limit theorem is effective, but not for all populations. This is that counterexample where you really need a higher sample size for central limit theorem to work well. Any questions, folks, so far about our exciting central limit theorem? Okay, well, what we're going to do next is look at this theorem again in view of example 4. This will be our last example for these notes. And to get through this problem, let's see, we've got about 6 minutes. Probably wouldn't be a good one for us to rush through right away. This will be a good one for us to come back to. Any questions at the moment, folks, then, before we call it a day? Okay, let me give you kind of a set of expectations for when we come back on Thursday. We'll finish off these notes. Then we're going to go to chapter 14. Chapter 14 is not going to be on exam one. It's going to really end right here. And so if you, at this point, do have some questions about the upcoming exam one, don't hesitate to throw them out there start of Thursday's class. So Thursday, we'll finish off any questions, finish off the notes here. That's going to be considered good review for the exam at that point. And if we have extra time, we're going to move forward into chapter 14. Well, I think this will be a good stopping point for us. If you have any questions, don't hesitate to hang out. Otherwise, have a great night, folks. Yeah, go ahead. There is. I haven't completely put it all together, but I expect to have it put together when we come back on Wednesday's class. If you check on Tuesday, it should be posted early as well. Yep, you bet.
I have a quick question.
Go ahead.
It's over the binge drinking question.
Oh, yeah, let me pull that one up. So this one right here.
Yes.
Gotcha.
Why is the parameter not the population proportion of all of like the
Oh, gotcha.
national wide students, not just like students at this college, I guess.
It's because of the sample. It's what really is kind of dictating what the P right here is going to look like. So the sample involves these 244 students. If we move backwards from there, let's see, it says 244 students. Actually, let's go from here. Sorry, let me try to highlight a little bit better. There we go. So the sample came from 244 students at one specific college. That means these students aren't going to be representative of the nation. They would have had to have been all over the country, essentially. The only population they would really be representative of is that specific college right here.
Oh, okay, that makes so much more sense. Thank you.
Yep, you betcha. Yeah, that's how it's very foggy a lot of times. But if you start with the sample, that's a good way to kind of reverse engineer what was our actual population.
Gotcha. Thank you.
Yep, you too. Gonna stop the share just for a moment to stop the recording.